Hello, I am Parham Amiri. Today I am presenting implementation of Chan-Vese Active Contour method for city bone segmentation. Today, precisely segmentation of bone pixels from CT imagery is of high importance, especially in applications such as computer-assisted surgeries or representation of 3D bone structures, in which minimal user interference and high accuracy are required. However, this is a challenging task due to inhomogeneous nature of bone structure, low contact on edges, and bone pixel values which overlap with other organs pixels. Different approaches are used to solve this problem, including global and local thresholding, level set methods, curved based methods, region growing, region competition, and watershed segmentation. Among these, we only will discuss global and local thresholding and level set methods in this project. Moreover, the other methods were not able to yield desirable and satisfactory results. Global and local thresholding method, we use a threshold to separate the image to layers, foreground or object, and backgrounds. The main idea of active contour method is to develop a curve which is subject to constraints from image to detect the object. For example, the curve around the object and moves toward its center and have to stop on the boundaries. In classical active contour methods, an edge detector is used, which depends on gradient of the given image. The classical active contours are dependent on initial contours and have limitation in low gradient areas. On the other hand, geometrical level set methods have characteristics which overcome issues such as initialization sensitivity and topology inadaptability. Between different active contour methods, Chan-Vese Active Contour method proved to best fulfills the requirements of uh, image segmentation. Chan-Vese Active Contour is an energy minimization method instead of edge detection, as is based on Mumford and Shaw minimal partition problem. Mumford and Shaw minimal partition problem wants to find a subset omega I of omega and U approximation of U naught or the image which varies smoothly within omega I and rapidly and discontinuously around boundaries of omega I, and if segmented image U restricted to be a piecewise constant function, or in the other words U be a constant in each connected omega I, then we have this formula for energy. And since C or our contour is fixed, the energy will be minimized when Ci is equal to average of U naught in omega I. By setting nu equal to zeros, Chan-Vese method wants to find a two-valued function U to best approximate U naught. And you can take two values, average of pixels inside C and average of pixels outside C. By having C as curve omega W an open subset of omega, we want to minimize this energy function with respect to C1, C2 and C, where C1 and C2 are two unknown constants. By applying level set formulation, first by defining C such as C equals to x and y, which the p of x of y is equal to 0, we have this formulation for energy. In this formulation, h is the Heaviside function and u naught is our given image. To minimize f, we set the derivative of f to zeros and use the Euler-Lagrange equation to update C1 and C2 repetitively. C1 and C2. Analytical approximation of model. We use this function to approximate Heaviside function and delta function, the derivative of Heaviside function. Or we can use the MATLAB code function of Heaviside instead. And this is the divergence approximation, where phi of x, phi of y, phi of xy are derivatives of phi. By having the definition of derivative, we have these formulas, and if we set the step space to 1, these formulas are yielded, and when we apply Taylor expansion to phi, we see the relation between phi n plus 1 and phi n. To sum, our most important steps of algorithm are computing phi 0 by phi naught, computes C1 and C2, obtaining phi n plus 1, recalculating phi, check whether the solution is stationary, if not, adding 1 to n and repeat. Experimental results. We apply thresholding method to a given image. We can see the results for 3 different thresholding values. The left image is our input image, the middle one is the segmented one, and the right one shows the manually segmented image by doctor. Value 0.52, thresholding value is 0.55. We see the results are better. Thresholding value 0.6, and we see the image is not good again. We can see the results highly dependent on the thresholding value, and it can vary from image to image. It's obvious that we cannot use thresholding as a separate method to segment a given image. However, we can use it to provide the initial contour to Chan-Vese Active Contour method for segmenting the image. We segmented 2 images using this method. This is the input image. We have to eliminating the fake edge, because the Chan-Vese Active Contour method we are using can only detect 2 layers. If we use Chan-Vese active contour, multi-phase active contour, this step is not needed anymore. And this is our initial contour, and this is the segmented image and the desired image. You can see that we have a good result here. The accuracy of our segmentation is 90%. And this is for another image, input image, the initial contour, segmented, and the desired. And the accuracy is 92%. Conclusion. We managed to automatically segment a city-bound image with a method combined for Chan-Vese Active Contour and thresholding. However, we need more data to validate this method because we only applied this to 2 images. Thank you for your attention.